Hydropower, powering the future with water. Welcome to our deep dive into the fascinating world of hydropower plant design. Today, we'll explore the key steps involved in designing the discharge for a hydropower project. It's not just about finding a rushing river and sticking a turbine in it. It takes careful planning and engineering to harness the power of water effectively and responsibly. So, strap on your thinking caps, grab your notebooks, and get ready to explore the ins and outs of hydropower discharge design. Estimating water flow. Go with the flow. First things first, we need to know how much water we're working with. This is the foundation of any hydropower project. Just like a gardener needs to know how much water their plants need, hydropower engineers need to figure out the flow rate of the river. It's all about understanding the resource at hand. Flow rate is the amount of water passing a given point in a certain amount of time. This measurement is crucial for planning. Think of it like measuring how fast a bathtub fills up. You're looking at how much water flows in over time. The faster it fills, the higher the flow rate. We can use historical data, like rainfall records and river flow measurements, to get a good idea of the average flow rate. This helps us predict future water availability. Now, to calculate the flow rate, we use a neat little formula Q equals A times V. It's simple yet powerful. Q is our flow rate, A is the cross-sectional area of the river, and V is the water velocity. Each component plays a vital role. Knowing the flow rate is crucial because it tells us how much power we can potentially generate. This is the key to efficient energy production. Rivers can be fickle things with flow rates changing throughout the year. Seasonal variations can significantly impact power generation. We want a system that's efficient and reliable, generating power consistently without being overwhelmed by high flows or starved during dry spells. Balancing these factors is essential. Now that we've got a handle on the river's flow, let's move on to the heart of the hydropower plant, the turbine. This is where the magic happens. Turbine time. Picking the perfect powerhouse. Alright, turbine time. Let's dive into the fascinating world of turbines and discover how we pick the perfect powerhouse for our hydropower plants. These mighty machines are the heart of a hydropower plant, converting the kinetic energy of flowing water into rotational energy that ultimately generates electricity. Without them, the magic of turning water into power wouldn't be possible. It's like a water wheel on steroids. Modern turbines are far more efficient and powerful than their ancient counterparts. But just like you wouldn't use a scooter to win a car race, we need to choose the right turbine for the job. The selection process is crucial to ensure optimal performance. There are a few different types, each with its own strengths and ideal operating conditions. Understanding these differences helps us make the best choice. For high-head, high-power applications like dams with large drops, we often use Francis turbines. These are designed to handle significant water pressure. Then we've got Kaplan turbines, which are like propellers in a pipe. They are highly efficient in specific scenarios. They're perfect for low-head, high-flow situations like rivers with gentle slopes. This makes them versatile for various environments. And for smaller-scale projects, we have Pelton turbines. These are ideal for locations with limited water flow but high energy needs. These use powerful jets of water to spin a wheel with buckets, kind of like a high-tech water wheel. Their design is both simple and effective. Choosing the right turbine depends on a delicate balance of factors, including the head, the vertical distance the water falls, the flow rate, and the desired power output. Each factor plays a critical role in the decision-making process. Once we've crunched the numbers and considered all the variables, we can select the turbine that will maximize energy production while ensuring the long-term efficiency and reliability of our hydropower plant. This careful planning is essential for sustainable energy generation. Now that we've got our power source sorted, let's talk about getting the water to the turbine efficiently. The journey of water is just as important as the turbine itself. Penstock power. Sizing up the water highway. Okay, picture this. We've got our roaring river, our perfectly chosen turbine is ready to spin, but we need a way to get the water from point A to point B. That's where the penstock comes in. It's like a giant water slide for energy. The penstock is a large pipe that carries water from the intake to the turbine. But just like we wouldn't want a traffic jam on our energy highway, we need to make sure the penstock is sized correctly. If it's too narrow, the water will have to flow too fast, creating friction and losing energy along the way. On the other hand, if the penstock is too wide, it'll cost more to build and may not deliver the water with enough force to spin the turbine efficiently. To calculate the optimal penstock size, we consider factors like the flow rate, the desired water velocity, and the allowable head loss. Proper penstock design is crucial for maximizing energy production and ensuring the long-term sustainability of our hydropower plant. Now that we've got our water flowing smoothly to the turbine, let's talk about the force behind it all. Head. Chapter 4. Head for power, the force behind the flow. Alright, get ready for some physics fun. We're diving into the fascinating world of hydropower physics. We're talking about head, and no, not the one on your shoulders. This head is all about water and energy. In hydropower, head refers to the vertical distance the water falls from the intake to the turbine. It's a crucial measurement. It's like measuring the height of a waterfall. The higher the fall, the more potential energy. This potential energy is what we harness. The higher the head, the greater the force of the water pushing down on the turbine blades, and the more energy we can generate. This force is what drives the turbines. To calculate the net head, we take the difference in elevation between the water surface at the intake and the water surface at the turbine outlet, and then we subtract any energy losses along the way, like friction in the penstock. These losses can significantly impact efficiency. The higher the net head, the more profit in terms of energy production. This means more electricity and better returns. Head is a critical factor in hydropower plant design because it directly influences the type of turbine we choose and the amount of power we can generate. Different turbines are suited for different head heights. Understanding head is key to unlocking the full potential of hydropower. It's the foundation of efficient energy generation. Now that we've got a handle on the power behind the flow, let's talk about how we get the water into and out of our hydropower plant safely and efficiently. This involves careful planning and engineering. Okay, we've got our turbine spinning, our penstock flowing, but how do we make sure the water gets into and out of our hydropower plant safely and efficiently? That's where the intake and spillway come in. They're like the entrance and exit ramps for our water highway. The intake is a structure that controls the flow of water from the river into the penstock. It's like a giant valve, carefully regulating how much water enters the system. Intake structures often have screens to prevent debris, fish, and other unwanted guests from entering the penstock. Now, on the other end of the system, we have the spillway. This structure acts like a relief valve, safely discharging excess water downstream, especially during periods of high flow or floods. Spillways are carefully designed to dissipate the energy of the water as it flows over them, preventing erosion and downstream flooding. Designing effective intake and spillway structures is crucial for ensuring the safety, efficiency, and environmental responsibility of our hydropower plant. Speaking of the natural world, let's talk about the environmental considerations of hydropower. Alright, it's time to talk about the environment. Hydropower is a fantastic source of clean energy, but it's important to remember that we're working with a natural resource and a delicate ecosystem. Building a hydropower plant can change the flow of a river, which can impact the plants and animals that call it home. One of the biggest concerns is fish migration. Dams and other hydropower structures can block the paths of fish swimming upstream to spawn. That's where fish ladders come in. These ingenious structures provide a series of steps or pools that allow fish to bypass the dam and continue their journey. We also need to carefully manage the flow of water downstream of the hydropower plant. Releasing too much water at once can cause erosion and harm aquatic habitats, while releasing too little can disrupt the natural balance of the river ecosystem. By carefully studying the local environment, consulting with biologists and ecologists, and implementing mitigation measures like fish ladders and flow management plans, we can ensure that our hydropower plant is a responsible steward of the environment. Okay, we've got our hydropower plant up and running, but how do we make sure it's operating at peak performance, generating the maximum amount of clean energy while minimizing any environmental impacts? That's where the magic of optimization and control comes in. Think of it like tuning a race car. We need to fine-tune all the different components to work together seamlessly and efficiently. In hydropower, that means using advanced control systems to regulate the flow of water, adjust turbine operation, and optimize energy generation based on real-time conditions. These control systems are like the brains of the operation. constantly monitoring factors like water levels, flow rates, energy demand, and even weather forecasts. They use this information to make adjustments on the fly, ensuring that we're squeezing every last drop of clean energy from the water while keeping everything running smoothly. These sophisticated control systems are essential for maximizing the efficiency, reliability, and environmental responsibility of our hydropower plant. And there you have it, a glimpse into the fascinating world of hydropower plant design. Thanks for joining us on this journey through hydropower plant design. We've covered a lot of ground, from estimating water flow to optimizing energy generation. Remember, hydropower is a clean, renewable energy source that has the potential to play a major role in our transition to a more sustainable future. By understanding the key steps involved in designing and operating these amazing power plants, we can help unlock the full potential of water power. Don't forget to like, share, and subscribe for more informative content.